Go ahead.
Oh.
All right, Yang, you can, ready to start?
Oh, yeah. So today we'll have Hu Sun, who is currently a first-year PhD student at the University of Michigan, to talk about some of his recent work. Who did his master's degree at the University of Michigan and has already completed a couple of projects on solar flare predictions. And today he will talk about an interesting matrix completion algorithm that we recently developed in the application field of space sciences.
Yeah, thank you, Jan, for the introduction. Very glad to be here to share our recent work on video imputation algorithm that we devised to impute a particular type of astrophysics images. So can everyone see the shared screen? Cool.
Yeah.
No?
Yeah.
Sure. I put on full display mode. Can anyone see the full screen mode right now? Is it good?
Looks fine.
It looks the same as before.
Oh, just 1 sec. Let me.
It was fine.
Right. There you go. Okay. So our topic today is video imputation prediction models in context of space weather monitoring. My name is Hu Sun, and here I list all of the collaborators who also participate in this project. Basically, there were two groups of people. One group of them come from Department of Statistics, and the other few come from Department of Climate and Space Science and Engineering, also at University of Michigan, Ann Arbor. Here I included a link to our preprint version of our work. You can click here if you want more details after the talk. Okay, so this is the presentation guideline for today. There were 4 sections. There was a background section, a method section, empirical analysis, and finally about conclusion and future plans. The title said it's video imputation and prediction model, but I will mainly focus on the video imputation part, and I'll put some of the discussions about prediction model only in the future plan. The first 3 sections give a general idea. The first section, background section, give a general idea about what the data that we are trying to devise our algorithm and apply upon, which is called total electron content map, the TEC map. And then I'll give some theoretical overview about the method that we're using in our framework. One of them is matrix completion. The other one is spherical harmonics, 2 very popular methods for imputing maps with missing values. And in the method section, I'm going to combine a lot of elements that are introduced in the background section to a combined conceptual framework and introduce what is our final algorithm look like, and provide some simple theoretical guarantees to show that our algorithm typically works well. And finally, I will showcase that how our algorithm works compared to the traditional matrix completion method, imputing a TC maps in using both simulation studies and some real examples. Okay, let's get started. So what is TC map? So TC map is ionosphere total electron content. It is defined as the total number of electrons in the path between satellite radio transmitter and a ground-based receiver. So the satellite comes from the GNSS system, the global navigation satellite systems. So you can see that the critical condition here is that there should be a ground-based receiver to measure what is the total electron content, right? And it is generally the case that not everywhere on the Earth has very good coverage of this global of this ground-based receiver. There are a lot of places in the oceans where we don't really have any receiver right there. So that kind of creates some data gaps where we do not really fully observe the global TC landscape everywhere on the Earth. It is more concentrated on the continents, and we have very rare observations on the oceans. So the TC values are typically measured by this so-called TC unit. And why it is important to monitor this TC map, why we bother to try to impute TC maps with missing values? Well, it turns out that the GNSS system is providing this PNT service, the positioning, navigation, and timing service, and the accurate reconstruction of TC maps can kind of improve the positioning accuracy of this PNT service. So because the TC kind of affects the propagation of radio waves leading up to some positioning area in the GNSS service. So we want to make sure that we have some very good technique that can reconstruct the global landscape of TC map across the globe to make sure that the PNT service is more accurate. But that's kind of the long-term goal if we finally put our algorithm into operational use. But this is kind of the motivation, the physics background for our data set. So this is what a TC map actually looks like if you focus on the very left panel. So there are 3 panels in this figure. The left one is what we call the Madrigal TC map. There were several databases containing TC map observations, and one of them, which is also of our primary interest, is the Madrigal database. So the Madrigal database contains high resolution global TC map, global TC landscapes. You can see that it actually covers all of the latitude and all of the local time range across the globe. And the white pixel, actually, you can see there are big patches of white pixels in these 2D images. These are the missing values where we don't have the ground-based receiver. So we don't have any observations in the ocean. It is more concentrated on the continents. There are some scattered observations in the ocean, but generally there are around 74% of the pixels in this high resolution image that is missing. So that is really bad. We don't really have a lot of observations globally. And typically what people do to just as a first step to reduce this data missingness is to apply some simple computer vision trick to impute some neighborhood which are missing for all of the observed pixels. So one of the method is called median filter, where you try to impute some missing pixels by using the median value of the neighborhoods. And this is kind of only it's not really a panacea, it's only kind of an intermediate remedy where it still significantly reduces the amount of missing pixels, reduces from 74% to 47%. It's kind of like doing a simple computer vision filtering, but overall, it doesn't really solve the ultimate problem where we still have a lot of big observation gaps in the ocean and also some scattered missingness on the polars and also on the boundary of the continents. So finally, our project goal is to give some imputation results to impute this Madrigal high resolution TC maps. But to make sure that our problem is not that tough, we've primarily focused on imputing this version of the TC map where we apply the median filter. So overall, the data missingness for our dataset is around 50% instead of the 75%. But these two are coming from the Madrigal database. There are some other alternative data source for TC maps. One of them is called IGS, the International GNSS Service data. So their data is kind of similar landscape. You have the coverage of all of the latitude and all of the local time. So it's a global map. But the merit of this data set is that it doesn't really contain any missing values. You can see that everywhere there is no white pixels compared to what we have in the Madrigal database, right? But the bad thing, the drawback about IGS dataset is that it is overly smooth. The reason why you didn't really see any missing value in this type of map is that they apply some smoothing method to provide this final data product. The other drawback for the IGS dataset is that it is particularly low resolution compared to the Madrigal database. Sometimes it loses some local structures of the TC maps that some of the experts would want to see in the TC maps, but is kind of absent in the IGS database, but is present in Madrigal database. So sometimes IGS can serve as an alternative to the Madrigal database, but because of these drawbacks, it is not really the most ideal version of the TC maps to put any analysis upon. We will primarily focus on the Madrigal database, high resolution image, but use some pre-processing step called median filter. So we have around 50% of the data missing. Okay, that's the background for our data. And bear in mind that there is still the IGS alternative. I will talk something about this IGS dataset later in the simulation study section. So yeah, this is pretty much about the dataset. So the goal
sorry,
of—
can I ask a quick question?
Yeah.
About the data. So these are actually estimates from true data that somebody has made, right? So what is the data actually like? What is the actual measurement being made?
The actual measurement should come from the definition of that ionosphere total electron content is the total electron along the path between GNSS satellite and ground-based receiver. So it is still measured in terms of this TEC unit, the electrons per square meter. And the resolution here is kind of like 1 latitude times the other one should be every 5 minutes of local time. So it is very, very high resolution. And in every pixel, if we have some observations, there should be a corresponding ground-based receiver to calculate that total electron on some.
Is it doing something like shooting a maser or something and looking at the dispersion measure of something like that? I mean, I'm trying to figure out what is the physical quantity that is being measured.
Honestly, I don't know about this physics techniques underneath, but it is still measuring the. The physics behind is kind of. Jan, do you have any idea about the physics background for this measurement, apart from the definition? That's the best I know.
No, I don't really know how exactly. What is the exact raw number? Because this is like, I think Vinay's question is more about, is it processed data or is it raw data? And I'm pretty sure it's processed data.
Yeah, and also
because some kind of summation needs to be taken.
There might be a few measurement sites per pixel to take the average, but I don't know the details. Did I interrupt anyone?
The reason I was actually asking this question was it depends on how the measurement is being made. You know, if you have a maser on a satellite and shooting it to various receiving stations on the ground, you can cover a lot more of the sky and the path length through the atmosphere, right?
Mm-hmm.
But I'm not sure if that is exactly what they're doing.
They need a ground receiver,
yeah,
in order to measure those kind of stuff. So that's why the land is covered much
they
better.
Also need something in orbit, right?
They have something in the orbit, but they also need a ground receiver.
Right. Yeah.
So it sounds like it's measure. It's just like an astronomer might measure a dispersion measure to a pulsar, which is emitting some radio signal. Except here, the pulsar is a satellite, and we're on the ground. So I think it's just the same kind of measurement, but man-made.
Man-made, right?
So it's measuring the total column density between the ground and the satellite of electrons, just the same way that pulse, by measuring the time delay between pulses from a pulsar, you would measure the amount of electrons along the column between Earth and the pulsar, I think.
Yeah, that's a column density here too. Yes.
Mm-hmm. Okay, so and still to follow up on what Yang said, that it's processed, but it's also an estimate from another potentially inferential problem.
Yep.
Mm-hmm.
Yeah. Mm-hmm. So yeah, the major goal for bringing out this data set is to show what is the scenario for the missing data around 50% and why it is generally missing on the ocean because of we need a presence of the ground-based receiver. Yeah. But all right, so the project is a data-driven project. The goal of the project is to reasonably fill in these missing values within the TEC maps. There is some prior work about doing imputations on the TEC maps, maybe not really on the Madrigal database. For example, one of the latest work on this use some deep learning based models for TEC map completion. And they rely on this IGS dataset a lot. So the IGS dataset, again, is that low resolution version of the dataset, and it's also overly smooth. So we don't really want to pursue, follow the same track. We want to still preserve some high resolution nature of the TC map, but directly imputing the Madrigal database. So that is what we want to do. And so that's pretty much about the data set. We want to find a corresponding statistical technique from the statistics community that corresponds to the scientific problem that we have at hand, which is to do the imputation. So the first method that we go to is called matrix completion. Matrix completion, if you're familiar with it in statistics, it is commonly used in collaborative filtering in designing recommender systems. So for example, matrix completion can help to infer what a user could rate a certain item that he or she never consumed. For example, on Netflix, they use this matrix completion method a lot, where they try to impute the missing values in this user item rating matrix. So you can infer what is the preference, potential preference of a user on a certain item so that you can make corresponding recommendations. We want to bring matrix completion to our scenario. It is kind of a natural transplantation. And matrix completion is an elegant mathematical setup like this, which is the classical rank restricted SVD setup. So all of the matrix completion problem, they are formulated in terms of a optimization problem. So here the optimization problem is formulated as follows, where we have the data xt, you can think of it as a TEC map observed at a time step t. So xt contains a lot of missing values. And we want to find an imputation matrix, mt, in place of xt so that we can fill in those missing values. And the mt, the xt minus mt, you can think of it as a residual matrix, right? The first term in this optimization problem is kind of an imputation loss, measuring how our imputation works on the observed values, on the observed pixels. So what I mean? Well, the omega t here is a bitmap. It gives value 1 to every entry if we have observations for that entry in xt and 0 otherwise. The p omega t is an operator to project any matrix using this bitmap such that the final projected matrix has its original value, all of the observed pixels, and 0 for all of the missing pixels. So the xt minus mt here is kind of a residual matrix, and we do this projection. So we only focus on how our imputation deviates from the observed values, and then we take the Frobenius norm to kind of a sum of squared error to measure how our imputation kind of deviates from all of the observed pixels. And then we put a regularization term here where we penalize the summation of the singular values of our MT matrix. We don't want MT to be really, really high rank. We want to kind of constrain its rank a little bit. And we put a regularizer here. That's the classical setup for matrix completion. And it has some well-known solution, which is also very elegant. So the MT, the optimal solution for this optimization problem, has the following form. We have a U matrix and a V matrix on the left and right-hand side, which are coming from the SVD, the singular value decomposition of the XT matrix. And then the D is a diagonal matrix containing all of the singular values, also coming from the SVD of XT. And finally, we have this soft thresholding operator to reinforce a low rank structure for the final imputation result. But overall, this is kind of a classical setup for matrix completion. Is also very elegant solutions directly coming out of the SVD of XT, the original data with missing values. We're not really going to use this setup, however. We want to use a kind of alternative setup, which is more interpretable. So in an alternative setup to the matrix completion problem, use this kind of factorization form, where we replace our empty imputation matrix using kind of a factorized form, A times B transpose. So we replace MT with AT BT transpose and put in to just substitute MT. And we still have this imputation loss. We don't want our imputation to be far away from the observed values or in all of the observed pixels. And we also penalize this, the Frobenius norm, this time, instead of penalizing the nuclear norm, the summation of all of singular values, we penalize a similar term. We penalize the Frobenius norm for the A factor and B factor matrices. And what one can prove actually that this has the same solution to the previous problem. Even though we are changing the regularizer a little bit from the nuclear norm to the Frobenius norm, we still have this SVD type of solution. We're going to use this factorization form instead of the previous form because it is more interpretable. Why it is interpretable? Well, you can think about it this way. So such a factorization setup has direct interpretations in the factor matrices A and B. For example, think about xt, the map that we want to impute, the TC map, is of size m times n, where m and n corresponding to, say, the number of latitude and the number of longitude. And each row in A and each row in B in these two factor matrices can be considered as the latent feature for every latitude and every longitude. So every latitude and every longitude now has a certain feature, which is of dimension r that we can set, which also determine the final rank of the imputation matrix. So the final imputation at any location, you have the corresponding latitude and longitude. The final imputation is going to be the inner product of the latent feature vectors of the corresponding latitude and corresponding longitude, because this is how we get the final imputation matrix, right? A times B transpose. So every imputation at any location is going to be an inner product of the two latent features. This is the interpretation of this factorization form. And we're going to adopt this form in terms of matrix formula completion to try to solve the TC map imputation problem. But this is not really the final version that we are going to use. The final version we're going to use is called the SoftImpute method. This is the backbone of our algorithm that we are going to develop later. So again, similar setup with the matrix completion problem we have seen before, the previous two versions. We have the imputation loss here, and we have the regularization term here. The only difference is that here we don't really have that p omega t term anymore. We don't really do the projection anymore. Here we have this xt hat matrix, which is kind of a fill-in version of your original data. In original data, we know that we have a lot of missing pixels. But in xt hat, we no longer have those missing pixels. Instead, we keep all of the observed pixels as it is. And for all of the missing pixels, we impute the missing pixels based on the imputation matrix we get from the previous iteration. This is kind of an iterative algorithm, where each time we try to update A matrix and B matrix iteratively. So we kind of fill in all of the missing values based on the imputation result we get in the previous iteration and use this new kind of optimization problem to try to update our A and B matrices even more. So it is not really largely different from the previous version of matrix completion problem, but this time the imputation loss is no longer calculating the imputation loss on the observed pixels, but it's also on those missing values, on those missing pixels. This is the final form that we're trying to adopt into our algorithm framework, which is called SoftImpute. We'll go back to this term a lot in the empirical analysis section. And this is also the benchmark model that we want to compare our method against. So what if I directly apply this SoftImpute method to impute the TC maps, right? If it gets good results, then we can call it a day, and that's our final data product. How it looks like? Well, this is the original TC map that we have shown, where we have a lot of missing values. Around 50% of the values are missing. And on the right-hand side, we are directly using this matrix completion canonical formulation, directly applied it on our TC map and try to get it some imputation result. How it looks like? Well, you can see actually that in the ocean where we have big patches of data missing, we have big gaps of missing data. The SoftImpute method do not really have a lot of information in that area, right? So the only thing he can do is to impute some background value, near zero value in these regions, which is pretty unreasonable from some expert perspective, because TC values also has some spatial continuities. So even in the ocean, it should have some high TC values that are closer to the continents. instead of just purely imputing them with background values. So this is not really ideal. That's the first drawback of SoftImpute method, where it cannot really handle big patches of missingness. The second thing, if you take a closer look at the SoftImpute result, you can actually see that there are some type of band structures for some columns. It kind of like some columns are really similar to other columns. For example, in these regions, you can see actually there is these kind of band structures for every column. A lot of columns are pretty similar to each other. This is actually an artifact of the SoftImpute algorithm, where the SoftImpute algorithm artificially creates some low rank structure in your final imputation result, which is not really ideal from physics perspective, but it's okay from an algorithm perspective because we already find the best tuning parameter for this method. So this is the best that SoftImpute can do on doing imputations of the TC maps. But you can see that actually there are many, many drawbacks for this method. It cannot impute the big patch of missingness, and it also has this low rank structure, which is physically unreasonable. So in our framework, we try to solve these two drawbacks by using two other methods, and we try to combine those two methods I'm going to talk about later with SoftImpute. So together we can get some improve the quality of the imputation result. So yeah, this is what SoftImpute can do. And another method that I'm going to talk about, which is also serves as a solution to the first drawback that I mentioned, where we cannot really impute reasonable value in the big patch of missingness. But this method, called Spherical Harmonics, it can fill in some reasonable values in these big patches. So what is Spherical Harmonics? It is another matrix completion method, but it is not really directly imputing a matrix. Spherical harmonics is approximating data distributed on some 2D manifold on a surface with a linear combination of several basis functions. So for TC maps, previously we visualized it as a matrix, but originally you can think of a TC values are distributed on the globe. And we use spherical harmonics to approximate this distribution of TC values on the surface, on the 2D manifold. So this is the result if we directly apply the spherical harmonics method to impute TC maps. This is also similar to matrix completion, where we can fill in all of the missing values. But you can see actually here, the spherical harmonics result have some overly smooth structure. You can actually see that there are some Gaussian types of imputation result where you have these two peaks and a valley in the middle. The merit of this method is definitely that we can fill in some reasonable values in the big patches of missingness, while at the same time guarantee some spatial continuity. You can see actually the imputed values in the ocean are closer to the values we observed on the boundary of the ocean along the continents. But the bad thing about spherical harmonics is that it kind of overly smooth the TC maps. So as an individual matrix completion method, as an individual imputation method, spherical harmonics is not really that decent, but it kind of provides some useful information in the big patches of missingness, which can actually serve as a warm start for our algorithm that we are going to develop later. So the good thing about spherical harmonics is that it can guarantee a certain degree of spatial continuity, a spatial smoothness. The bad thing is that it kind of guarantees too much spatial smoothness. So we just want
to have questions.
Yep, sure.
So in here, so for the spherical harmonics, right, you're smoothing the data, I guess. You're not interpolating the data. And how do you choose the number of harmonics you're using here? I guess if you put in more, then you probably will better capture the data, right?
Yeah, you're right. So this is how the spherical harmonics basis functions looks like. I just choose a few orders. What you mean is probably that we can extend this list a little bit longer to incorporate more and more basis functions so to approximate better. What we use it based on, we tune it based on cross-validation. So we randomly drop 20%, say, of the observed pixels, we drop it, and we only fit spherical harmonics on the rest of the 80%, and then check how our imputation result worked on the rest of the 20% to finally choose the best combination of the tuning parameters in the spherical harmonics method.
Yeah, so I have some experience with that too. one issue is like when you do cross-validation, just because you look at it, on the left, right, the original map, you have more action around the center, right, and a little bit over like Middle America or Central America. So if you cross-validate your data coming from the like from the side, a lot of them are just very smooth. If you do that, you actually over smooth things. So I guess what I'm trying to say is maybe if you just like when we do cross-validation, you cross-validate the data where the actions are. You get what I mean? You try to cross-validate the data coming from the brown, okay, the green, but not from the blue.
Oh,
that may help you a little bit better.
I see. So you're talking about cross-validation with a specific choice of the validation set, right?
Yeah. There's a possibility. Right?
Yes.
If the blues are dominating, then of course what you get, right, will be slightly over smooth as what you actually. I believe what you get here is a slightly over smooth on the right.
Right. Yeah. So the cross-validation is done based on a series of this map where we have more than just a single map. We do cross-validation on maybe more than 500 maps at the same time. And we randomly drop pixels. So in some of the images, I believe the pixels are dropped in this high TC value regions. In other images, we drop the background kind of TC values for validation purpose. So yeah, but I guess what you said makes sense, is that we have to carefully choose the validation set. It turns out that spherical harmonics does not really play that much role in our final framework. It serves as a warm start, even if it overfits a little bit. In some other application scenarios, we try to artificially lower the smoothness in the spherical harmonics dataset, and our framework still preserves some of the structures that we want to see. So, I mean, even if we have some over-smoothing in spherical harmonics, I believe it is not really going to bother too much in our final result. But yeah, the spherical harmonics itself is probably over-smoothed here. Yeah.
Okay. Yeah, I just have two more comments. So because I've been enjoying your talk a lot. But I have to leave early because I have other commitment. So my other comments is when you do matrix completion, right? You assume the data are coming from a regular grid. But here, what you really get is from a sphere, right? So the point there, not really regular space. You know what I mean?
I see.
Denser. Yep. You get points denser on the two poles, and then a lot less dense around the equator. So I don't know whether this is a big problem or not. It may not be a big problem. But I know there are other matrix completion techniques that are defined on a different domain, okay, not a rectangular grid. So I don't know whether it will help or not. Okay, another thing I just want to say is, so you heard about neatness?
No.
Okay, so it's like when we do not on a sphere, on 1D or 2-dimensional thing, we have Fourier analysis, which is similar to your harmonic analysis. And then we have wavelets, which kind of built on the Fourier basis, okay, wavelet basis. So neatness is the same thing, but it's for the sphere. So it's not really a base because it's over complete, but it can represent a lot of sharp turns and jumps on a spheres. So if you're looking for another method, neatness may be another way. It's just do neatness imputation. Okay, you can capture a lot of irregularities. Okay, thank you again. I'm going to shut up now.
Yep. Thanks for the comments. Yeah. So yeah, the current framework is still operating on the matrix format of the data. Even if we're using spherical harmonics, we first fit the spherical harmonics by wrapping the matrix back into a globe, back into a sphere. But then we unfold the spherical harmonics back to a matrix and use this kind of as a warm start of our imputation. Yeah, so this is pretty much about spherical harmonics, and the basis function is just a linear combination to do the imputation. Spherical harmonics can overfit, but it does just plays a role as a warm start by providing some key information in the big patch of missingness in the ocean. All right, so now we get every element that we want. in our conceptual framework, except one thing. But the one drawback for SoftImpute that I didn't address in the previous section is about that low rank structure. We have those type of band structure in the final imputation. How do we solve that? Well, we add another elements in our conceptual framework. We will see very soon. So our final framework is a combination of all of the things that I mentioned in the introduction section: matrix completion, spherical harmonics, and even more. So our final framework has the following features. First of all, it can impute multiple TC maps at the same time. So it is imputing videos. That is why I entitled my talk as video imputation instead of just matrix completion. And I use the matrix factorization formulation as the imputed matrix, just for the interpretability and also for the ease of doing optimization in the later algorithm design. I use spherical harmonics as a warm start. In the rest of the talk, I will call this warm start as an auxiliary data that we can improve our imputation result. We also penalize the matrix norm of the factor matrices, just like the matrix completion method, which is also serves as a softer constraint on the rank. So we don't really want our imputation result to be of extremely high rank. And finally, to solve that second drawback, where we have the low rank, the kind of band structure in the SoftImpute output, what we do is we explicitly reinforce the smoothness of the imputed result along the temporal dimension. That is actually the reason why we want to impute multiple TC maps at the same time. We want our imputation result to be temporally smooth. That later I'll showcase that actually this explicit smoothness that we introduce along the temporal dimension can partially solve that low rank type of band structure in the SoftImpute outputs. So you can see that actually we explicitly control temporal smoothness. We use spherical harmonics as a warm start to introduce some spatial smoothness. So finally, our method is a combination of the matrix completion method, which gives us the baseline result. And then we explicitly control for the temporal smoothness, and we explicitly control for the spatial smoothness. So together is temporally and spatially smoother than the traditional matrix completion method. So the final objective function, similar to the matrix completion problem, where we still have this imputation loss term at first. Then we have this matrix norm penalty tuned by lambda1, which is a tuning parameter. This controls the low rank structure of the output. So the first line is identical to SoftImpute, to all of the previous matrix completion method we talked about. Then we explicitly introduced a temporal smoothness penalty. So we don't want to make our imputations in, for example, at adjacent timestamps to be too different from each other. And finally, we have the auxiliary data penalty, where the spherical harmonics warm start comes in. So we also want to make sure that our imputation is not far away from the imputation result coming from the spherical harmonics, to ensure that our imputation has some similar spatial continuity as the spherical harmonics outputs. So this is kind of a conceptual framework. You can see that there are many, many components in the objective function. And to put it concretely, first of all, our model has a name we also put in our paper. It's called a video imputation with SoftImpute, temporal smoothing, and auxiliary data. So basically summarize all of the elements in our framework. We call it VISTA, and I will call our model VISTA in the rest of the talk. Oh, there's some chat messages. Okay. Okay, so this is the objective function, to put it concretely. So we want to impute capital T amount of frames at the same time, where each frame is going to be imputed by this factorization form. We have the AT and BT transpose for every timestamp that we want to impute. And we want to impute capital T amount of frames altogether. So corresponding to the conceptual framework, here is what we have. We have the imputation loss term. You can see it's just simply a summation across all of the T frames, the imputation loss. Then we have the L2 penalty for the A matrix and B matrix factors. Also take the summation across all of the T frames together. And then here comes the temporal smoothing part, where we don't really want our imputation at time T to be much different from T minus 1. The TC maps, they are on 5-minute cadence. So every map should be pretty self-similar, should be pretty similar to the maps 5 minutes later. And we don't really want our imputation result to be that much different between two adjacent frames. Finally, we have the auxiliary data where YT is the imputation result coming from spherical harmonics. So we don't want our imputation result to be too far away from the spherical harmonics outputs. And we also take the summation from 1 to t. So this is the 4 components corresponding to the conceptual framework that we have. And we want to optimize this objective function in our algorithm. The output of this algorithm, you can see actually is the imputation for all of the t frames altogether. And we have 2 T matrices, TA matrices and TB matrices to be optimized. Before I dive into the algorithm, finally, I want to give some interpretations about our framework. There are actually some alternative perspective to interpret our objective function or just our model using a Bayesian type of perspective. So we are kind of assuming that the XT, the TEC maps, coming from a normal distribution with the mean matrices defined by AT-BT transpose, the imputation matrix. This is a data generating model. If you view our objective function from a Bayesian perspective, and we have some prior distribution assumptions for AT and BT, which are mean 0, and the lambda 1, the tuning parameter for the matrix norm penalty, is controlling the variance, the relative variance of AT and BT relative to XT. All of these distributions are element-wise for every entry in the matrix. The temporal smoothing penalty is kind of assuming a random walk assumption for the AT-BT process. So you can think of every pixel in the AT-BT transpose is a stochastic process that we assume to be a random walk, where the lambda 2 is kind of controlling the dispersion of this random walk. And finally, the auxiliary data penalty is kind of assuming another prior of AT-BT transpose, where the mean matrix is kind of defined by the YT, which is the outputs coming from the spherical harmonics result. The lambda 3 is also controlling the variance, the element-wise variance for this prior distribution. So if you put all of these elements together, actually you can see that our objective function is simply minimizing the negative log likelihood, negative log posterior likelihood of XT. Well, not just XT, there should be T frames of the TC map. So it should be X1, X2, all the way onto XT. But we are trying to minimize the negative log posterior likelihood based on this Bayesian model. So you can see the temporal smoothness is kind of equivalent to a random walk assumption. The auxiliary data, why I say it is providing a warm start, is because it is giving a prior to the AT-BT transpose.
Question?
Yeah.
XT is supposed to be the total electron content, right? XT of the data.
Yes.
So shouldn't that be positive, definite?
Oh, yeah, that's a good point. So we do some pre-processing step to convert XT to a normal distribution scale centered at 0. And then we do some post-processing after we get the imputation result to get back to the scale of TC maps. Yeah, that's a good point. So XT should be a pre-processed version of the TC map.
Thanks.
All right, so that's conceptual framework and the algorithm outline. I want to go quickly about the algorithm. The algorithm is very straightforward. So in total, there are capital T amount of frames to be imputed at the same time. Every frame has its corresponding AT-BT factors. And we update all of the factor matrices in a cyclic way. So we first update A1, then A2, all the way onto AT, and then B1, B2, all the way onto BT. And then we kickstart another episode of the update. Each time when we are updating one matrix, we fix the rest of the 2T minus 1 matrices as constant. We only update one matrix at a time with a majorization minimization algorithm. In the next few slides, you can see actually our final algorithm is simply doing a least square when we're updating all of these factor matrices. But all in all, we're updating these matrices in a cyclic manner, and we're only updating one matrix at a time. It is kind of similar to coordinate descent type of algorithm. So for example, there's some more theoretical details here. So for example, in the kth round of updating, we want to update a certain matrix called AT. The current values for all of the other matrices are A1, A2, and AT minus 1. They're all updated already in this round. So we use their updated value. The rest of the matrices haven't updated yet because now it is turn to update AT. So we want to update AT by taking advantage of the rest of the 2t-1 matrices. We keep them as their current iterative value as it is. So we keep every other matrix other than AT fixed at their current iterative value and plug it into our objective function. And we can reduce our objective function into the following form, where this is completely a function about AT itself. Everything else is kept constant at its current iterative value. Here, there are the rest of 2t-1 matrices. We just keep it as it is and only update AT. So if you plug these matrices into the objective function, you can actually see that this is pretty much the same as our objective function, except that here we only focus on the timestamp t. We still have the matrix norm penalty. We still have the auxiliary data penalty, and we still have the temporal smoothing penalty. We also have the imputation loss here. The only optimizer, the only matrix that can change is AT. Everything else is fixed. But this is not really the final form of the objective function that we want to optimize AT upon, because this is not really convex function in terms of AT. It is convex for the rest of these terms. It is convex in terms of AT. The first term, the imputation loss, is not really convex in terms of AT. So it is really hard to directly compute the derivative of the first term with respect to AT. So what we do majorization. We find an upper bound for the first term. It's very trivial upper bound. The first term is this, the imputation loss on all of the observed values. We upper bound it by using a filled-in version of the XT matrix. So this is the original imputation loss. We can upper bound it by the term on the right-hand side, where you can actually see that we actually keep still measuring the imputation loss on all of the observed pixels, but we also measure the imputation loss on all of the missing pixels. Here, the omega t perpendicular here just mean the complement set of all of the observed pixels, which just is the missing pixels. So we want to make sure, we want to just calculate on the right-hand side, what is the imputation loss on both the observed pixels and the missing pixels. So what is the ground truth on the missing pixels? Because we don't really have any observations there. So we filled in the missing pixels with the AT-BT transpose coming from the previous iteration and use this as the ground truth to calculate this imputation loss. This is very trivial upper bound for the left-hand side because now we are calculating the imputation loss for all of the pixels instead of just the observed pixels. So the right-hand side should be no smaller than the left-hand side. But the good thing about the right-hand side is that finally, we can pull the AT out of this projection operator. And so this is convex in terms of AT. We do this majorization, replace the first term in our objective function using the right-hand side upper bound. And now the objective function, what we call it Q tilde, is a convex function in terms of AT. We can directly take the derivative with respect to AT, set it to 0, and just do a little bit of linear algebra to solve what is AT. The AT, how do we update AT is based on this definition on the right-hand side. It is very similar to at least the square problem, where we're trying to regress a ZT matrix on BT. But anyway, this is kind of the analytic form of our solution, where we do a majorization to upper bound our objective function in terms of AT, and then just take the first order derivative, set it to 0. We can get this elegant update formula for AT. We do the same thing for all of the AT, and we do the same thing for all of the BT. This is our final algorithm. I'm not going to dive into details about this algorithm. It contains some extra details that it didn't cover. But overall, I would say the take-home message for our algorithm is that we cyclically update every matrix in a cyclic manner, A1, A2, AT, B1, B2, BT. That's one episode of update. And we keep on updating all of these matrices until convergence. And every update, we keep the rest of the two T-1 matrices as constant. Only update one matrix at a time. And finally, every matrix update is a simple least square problem, where we first do the majorization, and then we do the minimization, which is simply has a closed form solution, just like a least square regression problem.
Just to interrupt briefly.
Yeah.
We are running out of time, so if there are results or something that you can show, that would be
Yeah.
nicer.
So
thank you.
that would be it. Sure. So let me speed up a little bit by diving into the empirical analysis part. So just like Vinay said, our input video is on a different scale. We have the TEC unit, but imputation algorithm we kind of assumed as a normal distribution centered at 0. So we do some classical standardization by using Box-Cox transformation to convert it to a normal distribution scale and to make it 0 mean and standard deviation 1. And finally, we reverse these pre-processing steps to get our output so that the output video is on the same scale as the input video. And I want to skip the simulation study then to directly go to all of the VISTA model that we are trying to fit on our final result. So our VISTA model consists of several different components. The imputation loss, the matrix norm penalty, the temporal smoothing penalty, and the spherical harmonics penalty, 4 components. And you can play around by just combining different components together by setting different combinations of these tuning parameters. So there are 4 versions that we want to implement on doing the final imputation. We have the benchmark version, where we only have the penalty on the matrix norm. We have the temporal smoothing penalty, but no spherical harmonics penalty. We said spherical harmonics penalty tuning parameter to be 0, so we can throw it away. We have the spherical harmonics formulation, where we don't have the temporal smoothing penalty, so lambda 2 is 0. And finally, we have everything together, put in a unified framework. So we want to measure how our imputation works by using this measure called relative squared error, RSE, where the xt is the original matrix we want to impute. The xt star is the imputation result. Omega t is the bitmap indicating the observed pixels. The RSE is calculated in this way, where we calculate the norm of the residual map only on the missing values and divided by the missing value on the missing values on the original TEC map. So how do we validate this on the real TEC map? Because we don't really have observations of missing values. So how do we do this? Well, to do our final experiment, we choose here, we choose 2 days of data to show our result. One is September the 8th, the other is September the 3rd. One is called the storm day because of this high energy level. The other one is called the non-storm day. And we tried the different combinations of tuning parameters that I just mentioned before, several different versions of our VISTA model. And how do we do validation to calculate that RSE, relative squared error? Well, because we don't really have any ground truth values on the missing values. So what we do, we randomly drop 20% of the observed values as a validation set and only train on the 80% of our VISTA model and calculate the RSE on these 20% that we randomly drop as kind of a validation set to calculate how our model works. And here's the result that I want to bring out. So the storm day, September the 8th, we have different versions of our model, SoftImpute, temporal smoothing only, spherical harmonics only, and also the full model, which is the final unified framework, combining all of the components together. And also as a benchmark, we also put spherical harmonics itself as a imputation method, just for comparison purpose. And following here, the second panel is the non-storm day. So let's focus on the storm day for quick interpretation. So you can see that actually spherical harmonics is overly smoothing, just as Thomas said. It is not really doing well on the test set, very, very large RSE, very large errors on the test set. Also in terms of MSE, imputation is also not really good. But temporal smoothing, spherical harmonics, and the full model, where we both have the auxiliary data, the spherical harmonics, and the temporal smoothing penalty, we're getting the best results that we possibly can in terms of both RSE and MSE. And we are doing consistently good in nearly all of the frames in this storm day. We're doing good in 98% of the frames compared to the traditional matrix completion method, and we're doing 100% of the time better than spherical harmonics. So this is really a marginal but significant improvements compared to those 2 traditional methods, SoftImpute and spherical harmonics. Similar trend has been observed in non-storm day, but I guess I'll just skip the discussion for that and go to some visualization. So this is the non-storm day result. The first panel is the original map, contains a lot of missing values. And this panel coming from the SoftImpute model. So it is a traditional matrix completion method. You can see that there is a band structure, low rank structure for a lot of columns, and also a missing patch in the ocean is not really imputed with reasonable values. Here is the auxiliary data coming from spherical harmonics, which is overly smooth. So itself is not really a good imputation method, but it provides some warm start information. Here, this is the temporal smoothing method, where we only add a temporal smoothing penalty on top of the SoftImpute matrix completion method. And we are partially erasing some low rank band structures. This is looking more smooth than the SoftImpute matrix completion outputs. And finally, we have the full model, which combines temporal smoothing penalty and the auxiliary data together. You can see that it's actually spatially smoother compared to SoftImpute method, and also provides some imputation with some spatial continuity in the middle of the ocean. And this result is also more temporally smooth compared to SoftImpute or Spherical Harmonics result. Similar trend has been observed for storm day, where SoftImpute do really bad on the patch missingness. Spherical Harmonics did okay, give some imputations there. Temporal smoothing can smooth out the low rank structure. And finally, combine these three model components together into a full model. We can impute some reasonable values in the patch missingness, and we can also erase some of these low rank structures. So it is more like a coherent, a contiguous block of TC, high TC value regions in the middle of the map. Okay, so to conclude my talk, we propose a new imputation method called VISTA, combining matrix completion method with softer rank constraint, temporal smoothing, and spherical harmonics in a unified framework to impute this so-called total electron content maps with over 50% of the data missing. We have matrix completion, which provides basic low rank structure of the imputation. We have temporal smoothing, borrows information from tech maps at adjacent timestamp and smooths the low rank structure to erase that band structure in the matrix completion outputs. We have spherical harmonics, provides a warm start of the imputation values, and especially at the big patches of missingness. And our empirical results suggest some improvements in both global scale and meso-scale reconstructions of the TC maps, which turns out to be more reasonable to these astrophysics experts on the TC map applications. So 2 future works that we want to do. First, we plan to release a data product containing imputed TC maps using our VISTA model for the complete solar cycle in the last 11 years. And then we want to do a matrix or tensor-based effector model or other machine learning methods to do TC map predictions using this data product. Because finally, what we really want to do is to construct a complete imputation prediction data pipeline for operational use. So we can both impute TC maps and we also can predict TC maps in the future. That's pretty much about my talk. Yeah, thank you.
Thanks, Hussein. That was a very interesting talk and technique. Any questions?
I have a question. So you keep you compared the spherical harmonic fit and said that it's always too smooth. But so from a physics perspective, especially in astronomy, we're always decomposing spherical signals into spherical harmonics. Like the cosmic microwave background is naturally projected onto spherical harmonics. It's just a map of this looking out on the sky rather than looking down on the Earth, but it's the same idea. So we know that we can decompose any function on the sphere into a expansion in multipoles, right? Multipoles L and M's of the spherical harmonics. So when you say it's too smooth, does that just mean you truncated the expansion at too low at a multipole moment? Too low?
Yeah. I'm saying it is too smooth because, for example, if you see the result here, directly using spherical harmonics is not really working well. And I believe most of these errors come from the fact that is not really creating errors in this patch missing area, but in this area where we only have scattered missingness, spherical harmonics is overly smoothing this region where it is kind of introducing too much spatial continuity in the regions where we have plenty of observations. That's where the majority of the error comes from. The spherical harmonics is an okay method to provide information on this patch missingness, but is not really that superior in providing information in the region where we already have plenty of observations. That is why I'm saying it is overly smoothing.
Let me
Right,
try
but
to answer Casey's concern. So
Yeah.
if you use high order enough spherical harmonics, you are able to capture a lot of the detailed information or the detailed structure, but that will also create some artificial structures for us if you include too much higher order in the spherical harmonics.
Right.
And that's the result of our experiments. The thing that we want to capture from those maps is both sort of like a global property and also some meso-scale structures, which are really important. But those kind of meso-scale structures may not be something that's kind of smooth, like what the spherical harmonics result is giving you, even locally.
Yeah, so I guess my question is, when you fit this spherical harmonic, or you project on the spherical harmonic basis, you have to choose some order of the expansion at which you truncate.
Yeah, I think
Okay.
the way that we choose it is to intentionally choose it to a relatively low order to make sure that it captures the global scale. And then the meso-scale structures will be captured by the other parts of the model. So that's why we only call the spherical harmonics fitting as an auxiliary data instead
Okay, but I meant if you just did spherical harmonics and that was
Yeah.
the only thing you did, wouldn't you choose the truncation of the order based on some cross-validation? You know, what is the correct L to truncate the expansion? And is that what you did, or did you just choose it to be artificially low?
Oh no, the direct to spherical harmonics is based on cross-validation.
Okay, so you've
Right.
chosen the truncation in the.
Yeah, and there's also like a lasso penalty type of thing they're going on, trying to do the automatic screening of the
Basis functions.
basis. Yeah.
Yeah, so if I might just follow up, you know, given that astronomers are used to expanding signals on a sphere in spherical harmonics, it's very intuitive for us to think in terms of expansions in the YLM functions. And so because there's a very, you know, the L tells you the scale of the fluctuation, right? So the multipole moment tells you how wavy that function is at a given order. So it kind of makes sense to us to truncate at a given L, like the L of your lowest or highest resolution. But the other method, this matrix completion thing, is a little bit more abstract, because you're saying your map is a matrix which is now the product of A and B, which are lower order matrices. And I don't have a physical intuition of what that means to decompose a map into a matrix product of two lower order matrices. Unlike with the spherical harmonic thing, I have a very intuitive sense of you truncate the multiple expansion at L, and L tells you the highest resolution you have in your map. Is there intuition, a physical or a spatial intuition behind this kind of matrix, the M equals A times B?
Right. So I put an interpretation here about the latent feature arguments. So the matrix view of the TC maps is kind of focusing on the energy level or the TC activity level for different latitude and different longitude. The A matrix contains all of the latent features for all the latitudes. The B matrix contains the latent features for all of the longitude. Although there are not direct interpretations for these latent features, what they represent, but the final imputation, because it is A times B transposed, so the final imputation at any pixel is the inner product of the corresponding latent features for the corresponding latitude and longitude if you take a look at its coordinates. So different longitudes should have different TC energy level, as you can see there. the final TEC maps, even the original ones, it is more active on maybe the North American and Asian continents, where you have high energy level in just the sub-intervals of the longitudes, and also for the latitudes, maybe it is more active on equator. So these A and B matrices contains the embedding of the latent features for each latitude and each longitude, so that this is not really directly physically interpretable for every particular feature, what it represents, but it kind of, the AB transpose formulation, this factorization formulation, is to take advantage of this latent embedding to get the final imputation, which is simply doing inner product. So I believe if you take a look at A and B matrices in our final imputation result, you can see that there are some latitudes where the latent features are more significantly larger than other ones, leading to higher imputation values in some range of latitudes, and the same thing for longitudes. Does that partially answer the question, like interpretations?
Partially. I mean, when you talk about latitude and longitude, do you mean when you have kind of forced the sphere onto a grid?
Right. This is, our map is 181 times 361. So it is a 1-by-1 grid. Every grid corresponds to one latitude, one longitude grid. So the final matrix A and B contains the latent features for these.
Yeah, I mean,
intervals.
that in some sense, it's a little strange to me because the data naturally exists on a sphere, which is not really matrix. And so the physical correlations you might expect to be related to physical distance on the sphere. And so, the angular, the distance between two longitudes near the North Pole is obviously different from the distance between two longitudes at the equator. So there seems to be some breakage of that spherical geometry when you do that.
Right, that makes sense too. I believe based on the empirical result, I believe some of these has been handled by the sparsity that we created in both A and B matrices based on this matrix, a norm penalty. But yeah, maybe I should take the suggestion from Thomas to take a look at some matrix completion method by directly modeling the data on a sphere instead of unwrap it into a matrix. Yeah, this is the current framework definitely has some of the drawbacks you have mentioned. It is not really a natural matrix setup where we just unwrap it into a matrix.
Yeah, but this particular database is actually converted to those to the longitude and latitude that we have. It's really not us who tries to work on the matrix completion, because that is really the requirement of the data product that we need to provide. So it's not on purpose not to work on the sphere directly.
Yeah, this is the natural setup for Madrigal and IGS database.
Yeah, that's how they give it to us.
Yeah, and it's also a natural input for our future machine learning methods if we just put in a matrix format. Yeah, this is.
I would also argue, Casey, that the spherical harmonic method, while it's kind of the spherical generalization of Fourier, right? So something that is more localized, as in this latitude-wise or longitude-wise dependencies. It's perhaps better in that it's not trying to find a global solution and run into ringing, that sort of thing. So it's like using wavelets instead of Fourier transformations to analyze image data.
No, sure. I just have more intuition for spherical harmonics and wavelets on a sphere.
Yeah.
Than this matrix decomposition thing. Well, I mean, I'm not saying it's wrong. I'm just saying I would understand the spherical harmonic analogy better.
I have one question about the spherical harmonic fitting. I mean, you literally fit the coefficients of the spherical harmonic, right? So, what do you use for the uncertainty or error bars on the on your TEC values?
Currently, we don't have error bars for and uncertainties provided for the TEC maps.
So how do you do the fit?
You mean when we are doing the imputations?
For the spherical harmonic case.
Oh, the spherical harmonic case, we in our data pipeline, we put it here that for the input video, we fit each frame with spherical harmonics with order and also a lasso penalty tuning parameter that we predetermined based on a validation set.
No, but what does fit mean in this case if there are no error bars?
It's just like if you run a simple linear regression, you don't really need to know the sigma. You can fit it. You can learn it from the observations.
So that's essentially the equivalent of doing chi-square without the sigma square. That might also give you an improper scale. Right? I mean, if the true errors are smaller than what you would expect from the fluctuations.
Can I ask about the this metric for this mean squared error, relative squared error? Can you go to one of the slides? Where's my video?
Here.
Can you go to one of the slides where you show the maps, like the input map? Yeah, like one of these. So I was just thinking that, what are you interested in? Are you interested in how accurate this thing is at imputing data in the middle of the ocean, very far away from like any known or any receivers? Or are you interested in imputing the data in like, I don't know, Indonesia or wherever there's like a lot of speckly dots around? Because I feel like the method might perform radically different in those two different cases, and also the comparison between how well spherical harmonic does versus the soft imputation and stuff. So maybe it might be interesting to have an error metric that is just based on like certain regions of the planet that you're interested in. Like if you just took the pixels in the middle of the Pacific Ocean and calculated your relative error, or you just took the pixels, whatever, a little bit west of there and calculated the relative errors, you might find totally different rankings among the different methods.
Yeah, that was the question that I asked my collaborator when we started this project. What is the region of interest and what is the quantity of interest? And actually the answer that I got is that there's actually no region of interest because every single imputing point will be of interest. And different people will use this generic purpose map in a different way because some researchers will focus on the polar region. And some of them will focus on the low density and some of them will focus on the high density regions. Because as a statistician, it's very easy to just look at the red parts in the plots and see those are the interesting regions. But actually for them to study meso-scale structures, actually the lighter blue parts are actually more of interest in many cases. So I would see this particular method as a generic purpose data product instead of like a targeted inference procedure, because I think you're very right in the sense that different models will perform differently if we only focus on one small mesoscale. And perhaps the spherical harmonics will be enough if you only look at one particular small region.
I think it would be really interesting to see this relative error as a function of the density,
the regions,
sampling density of like the sampling point. Because in the middle of the ocean, the spherical harmonic probably works very well. The reason why you're getting such a terrible fit is because it's like
it's in the dense parts.
Yeah, like there's some different weighting between the dense parts and the non-dense parts that might be like totally washing out
Yeah.
interesting comparisons.
Yeah, that's a good point. We should create another visualization which shows the RSE and MSE as a function of the local TC values or the local variations of the TC values.
I would say the local density of the sampling where the receivers are.
Yeah, that's a good point. Actually, the part that I didn't cover in the empirical analysis is simulation study, where we touch a little bit about what you said, where we try to compare different type of missingness in a simulation scenario where to see how different methods compare to each other, where, for example, we only miss a big patch. That's probably the ocean scenario that you mentioned in a real TC case, or whether the missingness is scattered everywhere. And it is pretty intuitive that the result shows if it's scattered missingness, spherical harmonics is not really doing a lot compared to temporal smoothness method. But if it is patch missingness, if we miss a great big patch, then spherical harmonics is the better method compared to temporal smoothing. So this is probably correspond to what you said, where different modeling components in our conceptual framework is kind of tailored for different type of missingness. Some of them are more about that scattered missingness along the boundary of the continents. Spherical harmonics is better suited for imputing the big patch of missingness in the oceans. And we want to combine them together because we don't really have a particular region of interest. So we want to make sure that we balance these two components in the final imputations.
Yeah, that's interesting.
Yeah.
All right. Any other questions, comments? We are
One other
almost.
small thing, just to follow up of what Casey was asking about this decomposition between the longitude and the latitude. If there's no reason, if there's no physical reason why like this electron density should be separable with longitude times latitude, then you could do something to get rid of all these like weird stripy features by just rotating the initial map by some random angle, doing your whole imputation and then rotating back and doing that, 100 times.
Oh, so you're talking about rotating such that every pixel does not really correspond to just one latitude and one longitude. So we don't really have that band structure for every column, and then we convert it back so we can erase these low rank structures.
Yeah, rotate the original map so that the Earth looks like this diagonal rectangle. Just do the normal vertical, horizontal imputation, and then once you're done, rotate it back.
I would say it should be still there if you're still using the matrix completion method. This is kind of an artifact of the matrix completion algorithm where you always observe these low rank structure no matter how you formulate what the interpretations you have on the two factor matrices.
Right.
The low rank structure will depend on your rotational angle. So the low rank structure may be no longer for every column, but for maybe some diagonals in this map, but it was still there. Right?
For any angle, you will still have those stripes, but the idea is you do this 100, you rotate it by a random angle, do the imputation, and then rotate by another random angle, do the imputation, and then you average the results, and that'll get rid of all those artifacts.
That's a solution for this low rank structure, but in that case, because we are also using the temporal smoothing part and the TC map is constantly drifting towards the right. So the temporal smoothing has to make sure that the original map is not rotated such that you can borrow information from exactly the same temporal neighbors in the adjacent frames. Yeah.
So there is a physical reason why things should be structured in latitude and longitude, like because the Earth is rotating and the weather is moving east to west or something like that.
Yes. So our interpretation A and B matrices, the latent feature arguments, is saying it's kind of over-parameterizing. First, over-parameterizing every longitude and every latitude, because we want to focus on the local structures, which spherical harmonics cannot do. So we can focus on just one longitude and one latitude and construct their features individually so that we can reconstruct some local structures. But the Yeah, that's the interpretation for our method. But the but finally, we also introduced this matrix norm penalty to kind of reduce the effect of this over-parameterization. So we first over-parameterize it, and then we put a penalty on this over-parameterization to introduce still some sparsity in the latent features that we want to construct. So I believe even though we don't really have direct physical interpretations for every longitude and for every latitude, but we provide enough parameters to model the local structures for every grid. And then we introduce a sparsity structure to make sure that we do not overfit. So maybe it is still more data-driven because we didn't really put any further structures on the A and B matrices, like, whether we reinforce the different longitudes, which are spatially close, their latent features should also be close to each other. We don't really have that type of constraints. It is more data driven. So, but I believe it is based on the imputation result here, there should be some spatial continuities even in the A matrix and B matrix across latitude and longitudes.
If it's not too computationally intensive, it might be worth it to try this rotate by random angle, impute, and then rotate back and see if you can still capture those, if it still works because of the local movements of the TEC is usually east to west.
Yeah, our current algorithm is pretty efficient. So yeah, probably we can try that to see if it is another solution for this low rank structure.
I mean, it would be like one last step after you do this whole thing. It would just get rid of those horizontal and vertical feet artifacts or whatever they're called.
Yeah, in that case, perhaps temporal smoothing it's just an alternative solution to that rotation angle solution. Yeah, but it's completely data driven. Do not really have a lot of interpretations beyond the latent feature argument that I have said in the vector matrices. Yeah, that's what we have right now.
Nice.
All right, thank you. Again, we have reached the end of our allocated time. Let me stop the recording.